Okay, hello everyone. Welcome to the last episode of GPU mode for 2024. Uh, we're going to be restarting lectures like sometime like in later January of next year, so don't worry at all. So today is kind of like a talk I've been personally excited about. Like I'm joined by one of my colleagues, Chanyu Liu, who works on PyTorch distributed at Meta, to talk to you about Torchtitan. So Torchtitan is like a repository for you to do large scale training like very easily. Like you can see here, like most of the code is written in Python. There's actually not a whole lot of code either. Like if you go to the Titan repo and you just like count the lines of code in it, it's about like 5,000 lines of code is like in pure Python. Uh, there's like a bunch of other stuff, like mostly like configuration stuff that like bumps it up to 8K, but there's like basically about 5,000 lines of like, useful stuff. Um, and what's kind of cool about it is that like despite being so short in terms of lines of code, it's a pretty sweet reference architecture that you can use to like try training on like 100 plus GPUs. So at least like within these docs, I think that the team has tried like 64 GPUs and 128 GPUs. Uh, I think Chanya, do you have bigger numbers in the paper, by the way, or was 128 the scale that you?
Yeah, so the performance.md is a bit outdated, and we have 512 GPUs experiments running on 3D parallelisms in the paper. Yeah.
I see. Let's quickly go there. Performance here. Um, oh yeah. So this is where this is mentioned. Okay, so going back here, um, let me see where to start. So yeah, let's go here. Let's go to collectives. So what's kind of interesting about having a repository that's just 5,000 lines of code is that it's plausible for us within like the next like hour or two to actually just like read the whole code base like a book and like understand it. So it'll give you like a very good idea of like what some of these repos like might look like. There is like unfortunately just like a tiny bit of background, like more theoretical background that we need to go through in the beginning. And after that, we can basically go through the details. So for some context, like the whole reason I got interested in this is I was just mentioning before the recording started that most of my career at PyTorch has been focused on single GPU work. And you can get a lot of mileage out of doing single GPUs. Like there's like a lot you can do. Where this is sort of like biting me a bit is that like we've been sort of working in public on like one of these like we have a new working group called Popcorn, where the idea is to train an LLM that can generate Triton efficient like Triton and CUDA kernels. And the idea being that like a lot of kernels sort of look alike and kernel authors are expensive. And so can we make it like easier for more people to become like systems programmers? And so the idea here is that like there's two aspects to it. Like one is of course like oh yeah, and if you want to learn more about this project, we have a website now. Just a few moments. Very quickly. Here. Here, yeah. So GPU mode, GitHub IO, Popcorn. If you're potentially interested in this, we basically describe sort of what are the core work streams. Like one is basically how do we sort of generate as much data as possible. So we're going to be starting like hosting public competitions on the server where people can like compete on writing kernels, and I'll talk about that more in some other lecture. But then there's also sort of the training aspect. Like let's say we hypothetically generated like a very large data set of kernels, like let's say in the trillions of tokens. Now what, right? And so the idea basically this lecture should help answer the now what side of things. I do want to say that like this is a bit different from all the other lectures that we've given, and that like I don't have any slides. I'm purely gonna be sharing my screen and going through code. And Chanyu is really here to basically keep me honest. And if there's any misconceptions I have about distributed, like Chanyu is really like more the expert here. So if you have any questions in chat, I'll be like reading them. Yeah.
Mark, just a
Yeah.
note. We already have some compute that has been provided for the popcorn, and I think we need more. And we are calling out for more people to help us out on this. So we are reaching out. But if you have pointers or if anybody in this community has wanted to help us out, let us know.
Yes. Thank you, Vikram. That's a very good point. So going back here, okay. So here's the idea, right? Like working on a project like this, there's like an inherent amount of ambiguity. For example, like it might be the case that we don't need large scale. Like it is plausible that you have a large enough data set and you run it like a continuous fine tune, and then you run it on like one or two nodes, for example, and then you're pretty much like good to go. The problem is just that like this is unlikely to be true, at least from the anecdotal evidence we're seeing, because the data sets that we're collecting are already on the order of trillions of tokens, and this is without like crazy algorithmic generations. This is without like basically trying to artificially increase the number of tokens or anything like that. And so it seems like we're headed towards a direction where the team needs to just become like much more experts at distributed training. Um, so I saw a question in chat, I think, which was around who's using Torchtitan outside of Meta. I'll let Tianyu answer that, but I did want to plug one project that I think is very interesting. So let me just go show you the Torchtitan repo. One thing that's quite unique actually about Titan is that like it's not a library in the sort of true sense, as in like it's really meant to be more of a reference architecture. And what that really means is that because it's very little code, we want you to copy paste it. Like, please plagiarize it. Please make your own changes and go like ship cool stuff. Like, it's really the intent is to show you how easy it is to do parallelism with PyTorch. And it's not really to support every other library or model or data set under the sun. Like, that's just like not the core interest of the team. So there's one project that's like I personally find very interesting, and I'm trying to convince the team to come give a talk to us later next year, sorry, which is like the Prime Intellect team. They borrow heavily from Torchtitan, and they basically used it to do these like decentralized like global runs. So this is like one use case I'm excited about. But Janyu, if there's other teams you want to flag, maybe worth doing so.
Yeah, thanks, Mark. Yeah, I think so the purpose of Torchtitan, as you said, is more like a reference repo, in the sense that people would copy clone from it and make their own changes. So one of the feature I think it's worth mentioning is that Torchtitan supports distributed training, but in an elastic way, which means no matter you're from a single node or you're having like 1K to 2K GPUs or even above, we can support them all. So there's really no restrictions when you can use it, when you can't use it. From the GitHub issues, we know that a lot of people are using it for fine tuning, or like they call it, continual pre-training. So to give you more concrete evidences, we've seen researchers and the industrial labs doing their own training using Torchtitan, including recently this Atom Mini paper come out, which is a new kind of optimizer. They explicitly mentioned in the paper they're using Torchtitan. And another example, I'm not sure if I can speak their names. They developed a industry-leading diffusion models, and they're through social connections, we know that they were developing it using Torchtitan as the backbone. So, like I said, it's kind of elastic, and there's really a broad use to Torchtitan. Yeah.
All right. So just sort of like so we sort of since we're asking like the why questions, it is very, I think Byron made a comment around like it being similar in vibe to GPT fast. Like, yes, it is sort of similar in vibe. I think GPT fast is what we mostly encourage people to plagiarize it and copy paste it. And the sort of user experience, like again, me not knowing anything, like knowing very little about distributed training when I first started like looking into the project a few weeks ago. If you just want to run your first distributed training run, it's really you just copy paste this command in. So you basically give it like a configuration file. Let me zoom in a bit more. You basically give it a configuration file and you like run a llama train script. And this config file will let you set all sorts of things from like different kinds of parallelisms to your data set to how often you want to checkpoint. We'll sort of go over those details in a second, but like if you've used like projects like Axolotl, for example, like this sort of user experience should be very similar to you. You basically set up like a mega config, and then you can share that with other people and share your training runs. Anyway,
you write your own, can you make sure it's super efficient? If that's not the case, maybe using DTensor might be more efficient because it's handled by the by us. Yeah.
All right. So I think like we can come back to sort of like more. So please keep questions coming. This is great. I have the chat window open, so like just very engaged. So I thought like what we might want to do next is just again, I just want to quickly mention, maybe let me go here. Like if you just want to run Torchtitan and see like logs locally or push them to TensorBoard or weights and biases, like literally it's just run this command. So like this will just work. I did want to sort of maybe start going through some of the code and kind of how I approached it. Like one thing I found interesting about this repo is that like I started contributing to Torchtitan like this week, and I found it really easy and just like merged like 4 PRs. Oh, Chanyu?
Yeah. So just have one comment on the lines of code. Yeah, thank you for doing the statistics. I don't even have the most update knowledge on that. I think one of the reason it blows up from 3K to 5K recently is because we wanted to start shipping this multimodal support, basically the Llama 3.2. But it's not there yet, but we already shipped some code, but the code is kind of very long, it's 1K to 2K. So I would say without that, it should be 3K lines of code.
Oh, interesting. I guess like Aditya is asking, how can I use DTensor and FSDP to implement self-attention? I guess like Aditya, you're like referring to like implementing like a ring attention sort of algorithm using DTensor. So if that's the case, I think that's possible. I think one of my colleagues, Tristan, had a PR open on PyTorch, like doing this, and I'm not sure if it was MERS or not. Maybe Chanyu knows, but it's certainly possible. Maybe Chanyu can comment more.
So I don't know what the question is on, like the fancy attention, like ring attention, or it's just the self dot attention. Can you clarify that? But if it's ring attention, we currently support it using like under the name context parallel. I think it might be the case that Tristan's particular PR wasn't get merged, but we officially already have it, another version supported using DTensor. Yeah.
Okay, very cool. So yeah, let's just like, I'm just gonna show you how like I would like go through the code. So like just like a bunch of stuff outside, there's like a bunch of stuff that's not too important. There's this like one script, train.py, and you can run the script even without installing Torchtitan. So it really is like just a script. So let's just like go over it quickly and see like what's going on. So the first thing is like something with regards to enable debug tracing on failure. So I think this is the deadlock thing, right, Chanyu? Like I think so, right?
Look, can you repeat your question, sorry?
So this is the code that like basically does what was it called? It's like something like the record flight tracer.
Oh, I see. Which part? Yeah. This part records your traces so that we have this thing called fly recorder to help you debug in a, like basically, for example, Nico timeout, such things which it's hard to debug in a distributed setting. Yeah. But that's only the first. That's only the wrapper, at record wrapper.
Yeah. Otherwise here, like basically we init a bunch of loggers. If you go to init logger, it's like nothing fancy here. Going back to the train.py, setting up colors, avoiding garbage collection. Setting garbage collection. Oh yeah, the set determinism thing is interesting. Like this only applies to data loading stuff, if I recall correctly, right? Oh no, for everything. Everything.
I think, yeah, we recently have a new PR to make it right. I don't think it's currently 100% right, but yes, this set determinism thing is like setting the random seed and determinism in a distributed setting, including multi-dimensional parallelisms. We initially thought it was not that difficult, but later on we found it's non-trivial when you combine pipeline parallel and other things like tensor parallel and other SPMD style parallelisms. Yeah.
So speaking of pipeline parallelism, maybe let's talk about that briefly. So there's this joke I think I saw like Carpathy make on Twitter like a while back, something like no code base survives pipeline parallelism. And that's just because it is like it's actually the hardest of all the parallelism strategies to implement. And as a result, you'll see in the code base, there's like a lot of like lines that look like this. Basically, if pipeline parallelism, do something, otherwise do something else. Which is why for today, at least from an educational perspective, we're completely skipping pipeline parallelism. And if there's interest, we can just have like probably a standalone lecture just on that. So let me go back here. All right. So back here. All right. So here, like, okay, so this is the world size initialization. And then the first sort of chunky piece of code is this guy, the parallelisms. So it basically seems like it takes as an argument, like by, what's the data parallel replication? Are we enabling context parallelism, tensor parallelism, pipeline parallelism, lost parallelism? And if we go to this thing, it basically seems like it's mostly a configuration object, right? Like it's a data class and it holds like ints. You basically build a mesh, which is like setting up like a dictionary with all these flags. And then there's a bunch of these properties enabled such that like if any of these properties is greater than 1, then it means it's enabled. So this mostly seems to play the purpose of a configuration object. I guess here, this mesh here, oh, but this does actually return a mesh though. This takes this init device mesh and then init device mesh. Oh, wait, 1 second. Yeah. And then what in a device mesh, it takes in like a device type and a mesh shape, which is basically going to be, actually, yeah, maybe Tony, do you mind talking a bit more about like how this works?
Yeah, sure. So basically device mesh is our abstraction of the underlying hardware. So basically you can think of it as a high dimensional cube, which you organize the hardware into FSDP groups, TP groups, and PP groups, so on and so forth, and they're orthogonal to each other. This init device mesh thing is just trying to handle the complicated stuff under the hood and give you a nice abstraction. And inside this device mesh init, you would set up this, find the right process group, find the right hardware, and initiate those if you're using, for example, NVIDIA GPUs, initiate the nickel communicators so that when you call, for example, dtensor dot redistribute and you want to change it, like for example, or reduce scatter, it knows where to find the right communication channels. So basically it's a nice abstraction.
All right, and then going on, we see this sort of device module set device. We have this utils and it distributed. Let's see how this works. Excuse me. Let's see, job config. So this mostly seems to be setting some optional debug flags, right?
Yeah, this is more like the fly recorder setup. You wanted to dump your traces somewhere, so later on you can see them, yeah, or use some tools to analyze them.
And then this mostly seems to be a wrapper around this function in PyTorch distributed, which is initialize the process group, which picks a backend from a string, presumably, but most likely this would be nickel in most cases, with like a timeout that we also generally configure as well. So actually, so maybe this is a good time since we're talking about timeouts. Like Aditya's asking, how do you handle GPU failures and redistribute training amongst other nodes?
So you're talking about more like a fault tolerance thing?
Yeah.
I think currently, if you're doing this SPMD style of training, fault tolerance is not handled, like by default, not handled well, which means any of your node fail or any of GPU failed, your total drop would fail. And recently, because the scale is getting bigger and bigger, there's more need for fault tolerant. And recently, the PyTorch team, especially our colleague Tristan, initiated this Torch FT as another repo to showcase how do you do it in a fault tolerant way? For example, if a node is down, can we detect it? Can we automatically bring it back up when it's ready? And we, like in 2025, we have planned to showcase Torch FT and those fault tolerant training in Torchtitan as well. So to answer your question, it's not ready yet.
All right. And then moving on. So now we initialize like a device. Is Torch FT public?
Did I say something which is not public? Can you search?
Maybe.
I believe it is.
Let me check.
Uh,
It is public. Okay,
Yeah.
hooray. Okay, we're not fired. Excellent. So yeah, so this is from Tristan again. I think he gave a talk recently about this at the PyTorch conference. All right, phew. And then how does this work? Oh, I see. It's just like it creates its own manager, distributed process group glue. Oh, the code looks very similar to what you would expect.
Yeah, it actually just wraps the thing so that you don't need to worry about the details. It's very nice. I've seen a demo on this. It's like super fancy. It shows you like some DDP ranks. Just you can kill it using a website API, and then you can see it instantly got killed, and several seconds later it's brought back up, and the loss and gradients are all handled like invisibly.
Yeah, very cool. I think because Tristan used to work on I think Torch Elastic before and Torch X where they did a lot of the stuff.
Yeah.
So this seems pretty cool. All right, so going back, where were we? Here. Okay, so we're gonna build this device monitor. So what is this? Yeah, device monitor. Okay, this creates a device memory monitor. What's a device memory monitor? And then, okay, so this is just like, again, like another class that like mostly handles figuring out like what's the, like basically all the VRAM stats that you might need, whether it's like max reserved, like max active. Actually, I was curious about asking you, like, because you mentioned that you don't do fault tolerance, but then you have this thing called number of ohms in the
Yeah, that's unfortunately I think like if your job wounds, then it dies, and you can't really it's not useful today.
Oh, I see. Okay. Okay. But basically here, like again, this is just like recording a bunch of data and I need tuples, so nothing crazy here. Oh yeah. So peak flops. Let's talk about flops MFU for a second. So the way this works today is like typically for a lot of like, let me just go to the main page here again. So if you go here, oh, sorry. This is a great video though, you should go watch it. But like here, I just want to show you these MFU numbers here. So for example, here, this is showing like an MFU number of 3% because this is like a toy debug model. And it's actually very common for like a lot of distributed libraries to share MFUs as a top level performance number. But I just want to caution you away from using that for like one simple reason, which is basically it's two aspects, like where we get peak flops here. So MFU is basically just like a measure of, like, it's supposed to be a measure of how effectively are you using like your hardware. And so typically, like, let's say for a specific data type, NVIDIA will say something like, okay, well, you have X flops that you can get at this D type. And so then you look at how many flops you actually got, and then you divide it by the flops that like NVIDIA reports, and you get a number. The problem with this is that, like, well, let's say some of your layers are in FP8, then and some are in FP16, this becomes kind of like a tricky formula to apply. And here, like, I should think, if I'm not mistaken, the MFU is calculated analytically as well. Yeah, here. It's a formula, right? Which is basically you look at like 6 times the number of params times number of layers, heads, and then I think Q's what's Q? I guess T is the sequence length, and then Q is, I don't know what Q is.
I forgot. It has something to do with it's a dimension divided by the number of heads.
Oh, I see. Okay. So the point being is that like different vendors disagree on how to calculate MFU. And even if you agree, like there's like analytical solutions for it, and people might agree with analysis. And then there's profiling based solutions where you actually look at the number of ops in your model. And then if you're using a different program, like the numbers will also be different. So this is kind of one of those things that like is useful as a baseline for you to know how fast you're running on your given hardware. But it's like much better to look at metrics like words per second, for example, would be like way more reliable and probably less fungible.
The 6 times number of params, that is an approximation, right?
Correct. Yeah. This whole thing is an analysis. Yeah.
I want to add a bit here. So MFU is different from HFU. I believe is hardware flops utilization, and this is model flops utilization. The hardware one is more like a physical one, like how many ops are you doing, divided by the peak flops. So regardless of if your op is useful or not, for example, you just do redundant computation, which is not useful at all, you still can boost your HFU. But MFU is like given a model, for example, a transformer model, you're supposed to like the minimum amount, like for example, there's no distributed setting, you don't have any redundant computation, you're just on a single device, and this is the amount you need to compute, and divided by the peak flops, and like logically, you would achieve this amount of computation regardless of how many actual computation you are doing. So this creates a lot of nuanced differences when you're using different, for example, different attentions. How do you define what's the needed amount of computations? It's not clear. So I would say, I mean, MFU comes out as a nice top line metric, but now it's more and more challenging given different variants, including the data types we're facing. So in Torchtitan, we try to keep the same as most of the popular repos, but like Mark said, you should be cautious when using it.
All right. So moving on, we've already talked about like these meshes, and notice here already how we have our first like if data parallel is enabled, then wait, interesting. Oh, so versus it's not enabled, then oh, I see. So basically, this is just saying if we don't have data parallel enabled, then we hard code the degree and the rank, so we don't have this problem. Similarly here, okay. So this is now, I guess, like the first like non-distributed side of things where we're building like a tokenizer and a data set. So let me just go over this very quickly. So wait, so I see, Eric, could you use kubectl to extract tensor core utilization directly from the hardware counters to estimate MFU, or does it have too much overhead? I guess, yeah.
Yeah, MFU has a definition. The definition is not really related to the actual count. Are you talking about the flop counter, which is also logical? But to answer your question, I think this is something. It's not really a measure of. It's more than a measure of how efficient you're using your GPUs, but also how do you compare your work with others. I feel there's a bit unfortunate thing that like we wanted to make sure our MFU computation is common enough so that people get a sense of what's going on. If we're using our own MFU computation, but others are not, I think the people will be misled when reading the numbers across repos.
All right, so back to the data set stuff. I think I want to show you like one thing. So first off, like at least for Llama 3, the tokenizer that they use is like tick token, and there's like nothing specific about distributed stuff here at all. Like this is just like any other tokenizer you might see. Granted, like what's interesting is like if your vocabulary is really large, like in the case of multimodal, you might need to explore things like, I don't know, vocabulary parallelism, but we're not going to talk about that today. The other aspect is like things like downloading the tokenizer. Again, nothing crazy. We literally just download it from Hugging Face with a bunch of like nice error messages. So like this is all, yeah, like nothing specific. The data set that we sort of, as an example, like most of the benchmarks that you're seeing were ran on the C4 data set, which is a pretty large data set. But if you want to sort of create your own data set, you basically need to implement two functions. Like one is like, where do you load this data set from? Often from the Hugging Face hub. And then how do you process it? As in like, how do you just like get pieces of text from it? And then in the case of C4, it's like sample text. And in the case of, let's say, I don't know, the Wikipedia, it might be a bit different. And then you essentially register your data set here and you're pretty much like good to go. So any text data set should work well. I haven't personally worked at all with multimodal data sets, so I wouldn't be able to answer. But at least like for anything text-based like CUDA kernels, this should work just fine. So back to train.py, we set up the tokenizer. Oh, Tenyu?
I just want to.
You should feel free to talk, by the way. Raising the hand will be too much, so just interrupt me.
Oh, okay, sure. I think you summarize it well, except that there is something distributed in this data loader thing, which that you wanted to load different data on different data parallel ranks, but you want to keep the same data on non-data parallel ranks. So that's I think it's worth calling out. And another thing is that you want to make sure your data loader is checkpointable in a distributed setting, meaning that if you like pause your training and having a checkpoint, you would resume from the checkpoint and you would not start from the first row of data, but somewhere you stopped earlier from. Yeah.
Yeah, I think in the data loading community, I've heard this referred to as like mid-epoch resumption. Like, I guess historically, if you're assuming you're doing multiple epochs per data set, it's not a big deal. But here, considering you have a single data set with 2 trillion tokens, like mid-epoch resumption becomes like much more critical. Okay, so actually, so where is that like logic? Like, it seems a bit abstracted away here. Like, I don't see. So is it just that like stateful data loader here? So I guess you were saying you want the same data, you want different data over multiple data parallel ranks, but the same over non-data parallel ranks. So I'm sort of curious, like where this is, where we can observe this, or is it maybe here in the stateful data loader stuff?
So like, can you go back to train.py when you call this? You can see we fit in this DP degree and DP rank. Basically, we like for different rank we give a different data, but when we fit it, we only fit in different, like only different DP ranks get different data.
Oh, I see.
So basically,
Oh,
under the single like same DP rank, it's like a device mesh, right? Under, like, for example, one row you got a same DP rank, but you'd get different TP or other ranks, and those ranks all get the same data because here they have the same DP rank.
Interesting. Yeah. So it's like this becomes the unique identifier, right? Like I think we see it here. Okay. I see.
Exactly.
Okay. Let's see. So building the model, I think, yeah, so this is like so right now, like this supports like variants of Llama 3.1. So this is like a model class. Like, let's see what this is. Okay, model class to Llama 3, and then transformer. Okay. So again, I don't think there's anything distributed aware here, if I'm not mistaken, right? Like this is just not like
that's the whole point. So this is the part where we're different from, for example, Mectron. We're doing this parallelisms in a model non-intrusive way. That you define your model and we apply different parallelism on top of it, but without touching it. Like without trying to not touching it at all. But sometimes we still have to, but it's rare.
Yeah, it's more like, I think I remember seeing some comments like in the code base, like we could make this intrusive change, but like we chose not to. I think I remember seeing 2 comments like that in the code base. Okay. So back here, how does this framework compare to DeepSpeed? Do you need to implement 0 on top of Torchtitan, or would it require internal changes?
So like I said, they are just different names. Basically, you can understand FSDP as 0.3. Although FSDP supports like multiple modes, some of them are closer to 0.1 or 0.2. So basically, you already have it. And to compare with DeepSpeed, I think DeepSpeed is in some sense a bit like Megatron, which has the core functions inside the repo, but here we don't have the core functions are sitting in PyTorch, and we just use them. And one of the biggest differentiators, I guess, is we try to make our techniques and code base easy and simple while being composable in the sense that multiple training techniques can work with each other. I'm not too sure about DeepSpeed and Megatron right now, but last time I checked, they may not necessarily have all the. For example, previously, if I remember correctly, DeepSpeed doesn't have tensor parallel, and Megatron doesn't have 0 or FSDP. I guess now things could have changed, but I think composability is definitely one of the thing Torchtitan features. Yeah.
All right, and then okay, let's talk about the meta device and its stuff a bit. So here you notice like there's this context manager. It says where Torch device meta, and then you instantiate the model from a meta device, and presumably this is because the model is too big to be instantiated on a single device before it gets sharded. So you want to instantiate like a fake model, and then shard it. Okay, and then moving on, there's a float8 handler here. So I will say like float8, the repo has support for float8. Maybe let's go there first quickly for a second. So float8 is functionality that's available on like SM89 and plus. So I think 4090s, H100s and plus should support a float8. The main thing to keep in mind, because I've seen people get bitten by this a few times, is float8 is primarily useful when your like matmul shapes are quite large. So it's like if you're running very tiny models, it's not like in 4 where this is like useful for local LLM workloads. Like it's more that like it is useful for training larger, like training the larger models. And if I'm not mistaken, Chanyu, I don't think you've enabled float8 for Llama 8B, for example. I think it's only for 7EB plus, right? Let me check.
Like as far as I know, I think you can check out the experiment results in our Torchtitan paper. Float8 even on Llama 8B accelerated it a lot. Not just because of this float8 linear, but also because, or more importantly, because we have this float8 all-gather, means that you're doing the communication with half precision. It's super fast. Yeah.
Oh, interesting. So this would be 8B, but maybe like when the data parallel rank is larger than a single node, perhaps?
8B, let's check out the numbers. I believe
Yeah.
within node it's also significantly faster. Let's check out the paper. We don't have it here. Sorry. Scroll up a little bit. This is the first page. Let's go to the experiment section. Yep. Scroll down a bit, and the first table you see. Yep.
Oh wow, 50%. I see.
Yeah.
Okay. Interesting. And then so this is Llama 3.1 8B on 8 GPUs with mixed precision training, selective activation checkpointing, and a local batch size of 2 with a global batch size of 16. I see. And then if you hear it's also 8.1,
but on
8.1.
128 GPUs.
Okay, same local batch size, larger global batch size, and you saw even like more dramatic speedups. Interesting. Okay, so really it seems like it is useful even at the 8B scale, and then as you sort of increase your data parallelism, it's still like you'll see even more speedups. Interesting. Yeah, so I think here so Chanyu also referred to basically enabling all gathers in FPA. So this is like also just like a flag. And then this is basically making sure the compute is happening in float8, and then this is the communications happening in float8.
Yep, and currently it only supports matrix multiplication, not I think it's not supporting SDP, like the tension.
Ah, yeah, that's correct. Although, like, I think there's sort of like, at least within Torcheo, like an early PR that I think Jerry Zhang has been working on, which is enabling float 8 STPA, with the core idea being like converting the QKV to float 8 before doing STPA. So hopefully this should be landing soon. Okay, so I think I'm seeing a question. Do we notice any benefits on L40, or is this primarily on H100? Let me,
I don't know for sure, but I heard it's only for H100.
what VRAM does this thing have? Oh, 48, I see. Yeah, I don't see float 8 mentioned here. Yeah, I don't see it. Anyway, let's keep going. A lot of these utils, like for example, like logging the model size and all that, this is like all very standard stuff. This is the sharding. Okay, so this is kind of like maybe the first really interesting part, which is like here. So again, we're skipping pipeline parallelism. We have these parallelized functions, and basically everything interesting in the repo is mostly happening in this file called, I think it was called
Parallelized llama.py.
yeah.
Yeah.
So this is the file that sort of like describes like all the different parallelism strategies, but like parallelized llama basically takes in a model, it takes in a mesh, which will describe like all the dimensions by which you're parallelizing thing. Okay, so I see a question, Santino. As far as I know, enabling tensor parallelism pipeline functionality for custom models and frameworks like VLM, TensorRT require model reimplementation in their APIs and layers, like the QKV parallel in VLLM. For Torchtitan, this architecture modification is done on the fly by the framework, or will there be a list of supported models for which this works? What exactly do you mean by non-intrusive to the model class?
That's an interesting question. So I'm still trying to understand what do you mean by custom models. So I see you mean basically a new model.
Yeah.
So we are just showcasing the Llama model in the Torchtitan, and the way it works that you bring your model and we apply those parallelisms on the fly, basically. Um, and the way it works is that the API were designed to not require model code changes, except for example, minor changes like, for example, when you use pipeline parallelisms, when you split, yeah, okay, we decided not to touch, but let me just touch a bit. So you split your model into several chunks, and for some of the layers, it may not exist. For example, the output layer may not exist on the first chunk. And then we have code like if if output layer is there, then we do something. We do the initialization or we do the computation. Other than that, we don't touch the code. And if you ask me, I want to bring a whole new model to, for example, Torchtitan. Can I still do it this way? I think most of the case you probably can, unless a lot of things, our focus has been on this, for example, language model. Let's say today, if you bring in a vision model or some Mamba model, you can check if it's like every single op is fully supported. But if it's not, we can always support in the Torch core, PyTorch core repo. So our goal is to not having any intrusive changes to model code at all. Yeah, but like again, like people can do whatever they want. Sometimes it's just harder, sometimes it's easier. But we believe like at least Llama 3.1 gives you a very good example. It's super popular and we can do it. Yeah.
All right, so I see here, for example, the first thing you check in parallelized llama is checking that tensor parallelism is enabled. Is there any reason why the order matters? Because you sounds like, yeah.
Yes. That's very interesting. So sometimes the order of applying does not matter, but sometimes it does matter. For example, when you combine tensor parallel and FSDP. Basically, you would you have to understand what TP does and FSDP does to understand what's going on. We apply TP first because we want to apply FSDP last, because FSDP is just a distributed storage, and you want to perform the altogether on the FSDP when running the training, for example, in the forward. You want to run the FSDP altogether to gather the whole TP-ized module to perform TP. That's the reason why FSDP is applied later than TP. So basically, you wanted to understand what's going on when they are composed together to decide the order.
And interestingly enough here, I noticed that TP has a few interesting flags here. Like one is for lost parallel, one is for enable flow date. So maybe for lost parallel, if I'm not mistaken, for things like a popular loss function for LM training is like cross entropy, and cross entropy over a large output will be very slow. And so instead you can basically just do the cross entropy in chunks of the output. Is this the idea? And why is this a flag for tensor parallelism specifically?
So loss parallel is a technique which allows you to do sharded computation when your vocabulary size is huge and you want to shard on your vocabulary dimension. It's you can basically we enable it in TP by default, but basically I would say it's a good addition, a good feature on top of vanilla TP. TP plus sequence parallel usually shards things on the sequence dimension, but the loss parallel shards the activation, the output on the vocabulary dimension. So you can think of it as a bit different, and it requires some dedicated implementation to it. It's there, and we enable it by default. I guess it's okay that we just disable this flag at all and enable it by default. Yeah.
And is there any reason why TP needs to be aware of FP8? Like for example, why not have something like if FP8, then convert the layer to FP8 and then do TP? So why does TP need to be aware of FP8 stuff?
That's a good question. I probably don't know this, but when applying TP, so basically the way FP8 works with FSDP is that FSDP has to be aware of what type of communication and matrix multiplication you're doing. But for TP, I guess the thing is similar, is that we have to be so basically the TP works in a way that you give me a module, I wrap you, but insert some hooks so that I know what kind of communication I want to do when doing execution. I guess so. My guess is FP8 is similar in the sense that the certain type of communication or computation going on needs to be known by the module itself. So that's the idea, but I didn't implement this part, so I don't know for sure.
Okay. So I think the next thing you check for is, do you want to talk about async TP, or do you think that's just like a
Oh yeah, that's
topic?
a very, very interesting feature. So basically by default, when you apply TP, you have blocking communication, meaning that before you finish this communication, you cannot start your execution. But by splitting the matrix into multiple pieces and perform some part of multiplication before others, you can simultaneously do communication and computation. And this feature is implemented in PyTorch using the so-called symmetric memory, which is bypass the usual way like Nico was doing those communication and memory allocation. So it's actually a feature that's quite innovative, and then I encourage people to check out. It basically makes it easier to access the memory on the other GPU.
So it sounds like the next thing that you check for is for activation checkpointing. So maybe let me talk about that for a second. Is it clear? Apply AC to transformer block, apply AC to transformer block. Where am I here? Oh, I see. I think, okay, so activation checkpointing is essentially like a technique to like, if there's certain ops, like at a high level, instead of like saving all of your intermediates for a backwards pass, you can recompute ops if they're not very like time consuming to run them. So for example, examples of things that you always want to save are like things like matmls because they're time consuming. But like, let's say for a thing like maybe something like a softmax, like, maybe it's okay that you don't save it. So I think, so by the way, like for selective activation checkpointing, do you know, is this like a hard-coded list or is it like a profiled list? Like, or do you just expect people to copy paste this list?
So we offer 3 modes of activation checkpointing. The full activation checkpointing basically bypass everything and recompute everything, which is not like maybe not cost effective. And we offer 2 ways of doing selective activation checkpointing. The first one is layer based, basically for how many layers do you do this activation checkpointing? And the last one is the one that I recommended is this selective, the operator based, this what you just described. And this list is based on like some offline, ad hoc, not ad hoc, but some offline studies like benchmarking is not something that's it's just hard coded based on our experience. And we are about to have a more advanced version of checkpointing, which is auto SAC, which is profile. I guess it's more profiling based to automatically detect what op you want to save and what to recompute. It's not yet in the main branch, but I think there's a PR on it in Torchtitan. And also, I think we're writing up a paper about it as well.
Oh, very cool. So where were we? I think, yeah, there is a, so I think after checkpointing, you applied compile, and it seems like the way you apply compile is over individual transformer blocks, not over the whole model.
I can explain a bit on this. So ideally, torch.compile is applied on the whole model and get the acceleration in an invisible way. But as of today, the way like FSDP implemented and torch.compile implemented, it's a bit tricky. Sometimes this like communications with like those FSDP techniques like this would cause graph to break in the sense that the compiler cannot trace into it and thus cannot provide you with the performance you want, and maybe even make it worse because the compatibility issues. And the way we're doing this right now is applying torch.compile at transformer block level. This has 2 benefits. The first benefit is that within a transformer block, it's a full graph, which means the compiler knows everything. It can gives you the ultimate speed you want, and also the FSDP is also applied at transformer block level. So basically, the prefetching, which I mentioned, at runtime you all gather a piece of model, so you can do the computation, happens on the transformer block level as well. So it can still have the expected behavior. So this is something related to FSDP, which is you don't wait until the last second to fetch the thing you want to do computation upon next. Basically, when you're doing computation on transformer block, say I, you simultaneously do the prefetching of the transformer block I+1. So basically, overlap them together. This behavior may not be that sound when you apply torch.compile on the whole model, but if you're applying this way, we still keep the behavior, so it's still super efficient. This is the first benefit I want to mention. The second benefit is that torch.compile recently has a new feature which allows you to compile only once for repeated structures. So if you apply torch.compile on several, say 32 transformer blocks in a Llama 8B model, then you would, under the hood, you would only do compile it once rather than 32 times, which saves the compiling time. So this is basically why we're doing it this way.
Got it. Okay. So then let me go back to where this is used. Okay. So we apply, okay, so we did TP, we applied AC, we applied compile. And now we're looking at FSDP, it seems like. Yeah. And then for FSDP, we have two ways of doing it. It seems like this is like some BC issue. Like maybe this changed, it sounds like, or something.
It's not actually BC issue. It
Oh.
requires the latest changes. Also, again, there's a recent PR to make everything much simpler for this part. So I encourage to read after the PR lands. But here it's basically saying it relies on some new features, which may not be in a stable release, but in a recent nightly. And it's basically reminding you, if you don't have the nightly, please install.
Oh, I see. And is this like basically because it sounds like if you're on stable instead of nightlies, you're not gonna support like these ND meshes, and so instead you
So
flatten them?
basically, this is a fallback when you don't have the recent nightly, which allows things to be simpler. We're still doing the like less efficient way, but yeah, like with the new PR, this would be removed. Yeah.
Okay. And it sounds like the last thing that you do is apply FSDP. FSDP takes a model, a mesh, the param D type, the reduction D type. Oh, I guess so. This is for mixed precision training policies. And then it also needs to know if TP and PP were enabled and CPU offloading. This is interesting. Like, how come it needs to know if TP was enabled?
I forgot. Can you check where it's used?
Yeah, let me see.
It's not used. What?
It's not. Oh, wait. Yeah, it doesn't look like it's used.
Wait, what? I should remove it. For PP, I can explain PP. So
If
yeah,
someone
they
wants their
decided not
first
to talk
PR,
about it.
if someone wants their first PR to Torchtitan, you can come to line 341 and do this. We'll merge it for you.
Yeah,
Anyway,
I don't know when it's shipped in. Yeah, it looks like a good first issue. Sometimes it needs to know what others are doing just for composability. For example, in PP, I know we're not talking about it, but PP would like in order to make them jointly when combined jointly and still giving the best performance, sometimes you have to configure FSDP a little bit differently, and knowing whether PP is there is helpful when choosing the best behavior. For example, this reshard after forward behavior for FSDP.
So looking at this apply FSDP function, it seems like we apply fully shard on individual transformer blocks, and then we apply fully shard on the whole model after that. Like, what's up with that?
Yeah, this is the thing that I just mentioned, right? So for FSDP, there's a granularity decision on when would you, how large of thing you prefetch, right? If you prefetch at a too large of scale, for example, at the model scale, then you end up doing like DDP, but with stupidly an altogether of everything in the very beginning, which is kind of defeat the purpose of doing FSDP at all, right? You're not doing like you're not saving memory, but you introduce communication. But on the other extreme side, if you shard at like doing altogether at the finest level, those communication, there'll be a lot of communication, it will kill you. So basically, we want to choose the right level of doing this. We call it bucketing, like how, like at what granularity do you do this prefetching. And the fully shard API, which is the FSDP2 API, do it in a like recursively wrapping way. And basically here we're wrapping at transformer block level first and doing the whole model. It basically means other than the things not in any transformer layers, for example, the embedding and output, which you fetch in the very beginning, are the things that you would do prefetching at transformer block level.
So I guess here, let me go back to apply FSDP. All right, so after that, we basically print a few logging statements. And interesting. Oh, wait, so this is Where's this if? This is if okay, so if there's no sharding, then we just use DDP basically. So this is yeah. If there's no sharding, we use DDP, and applying DDP. Go here. So for DDP, we check if there's compiled autograd. I don't really know what that means. And then I see the replicate function here is where? Oh, interesting. This is not DDP. This is not like PyTorch distributed data parallel. This is just like something else, right? The replicate function here.
I believe it is.
Yeah.
I believe it is PyTorch DDP.
Because it's in the composable namespace, which is the or
I don't have up-to-date knowledge on that. And also I think DDP currently is not composable with other technique like TP or PP because partly because it does not make a lot of sense to do so because usually FSDP is the first parallelisms you want to have. So you typically wouldn't go beyond to TP or PP before applying FSDP at all. Yeah.
Oh, actually, maybe I think you showed this really well in the paper. Maybe I'll show it to people. Here, like basically, if you're like want like a checklist of when to worry about each technique, like I guess for most of us, and I would say myself included, like I'm definitely in this bucket. I know there's a big range. Yeah, it's like, but at least like for me, like at least like within the popcorn workloads, like I suspect we're gonna be like on the 60 to 100 GPU scale if we manage things. You wish you had the problem scaling to 4,192. Yeah, I think the very few companies can, unfortunately, but I guess this is kind of what makes like, like the sort of community-based approaches for dispute training kind of a miracle that they can even work out. But I agree with you in that, like,
I think I agree with all this, but I think recently we introduced this context of parallelism, which could be useful even without going to the super large scale. FSDP could hit its limitations because of several reasons. I think here we're more mentioning the throughput reasons. Like before, for example, 500 GPUs, you wouldn't hit the throughput limit or throughput constraints caused by FSDP, but there could be other reasons, for example, memory reasons. And memory reasons could be due to like you have a super large, like giant model. For example, the Llama 3.145B model, which probably most of people wouldn't hit at all as well. The other is like on activations. For example, you have a super long sequences, and this context parallelism could very well kicks in to help you even within a node. Let's say you have a super long sequence which you cannot fit on a single GPU. Then why not use CP together with FSDP or without FSDP? So the landscape would be different. But since the CP comes out after the paper is written, so we didn't include it in the paper. But just to remind people, yeah.
all right, yeah. So let's go back. Let's see. Okay, so I mean, we went. I think maybe now that like we went through like the two main files are really train.py and parallelized llama. So maybe let me just do a quick scan of all the other ones. I think this is the multimodal stuff that Tanya was referring to. This is a long file, actually. I just realized. Oh wow. Okay, okay, interesting. I didn't realize.
This is purely because two reasons. The multimodal part is just the long, and the other reason is we have some doc strings which I thought like maybe people won't find it useful. But so yeah, as we're supporting more models in Torchtitan, we inevitably will have this issue if we want have the code natively sit in the repo. Yeah.
All right.
I wouldn't say it's an issue though. Sorry.
Yeah, I agree with this too. So other files, like I think this is back to the Torchtitan is meant to be a repo that you copy paste. Like, there's a couple of norm functions that are used, like I think like RMS norm and layer norm, which are very popular in these models. So, if you want like yet another one, we probably wouldn't merge it, and we would just like encourage you to just, add like your own like favorite norm layer here. I think there's also this sort of, I think one of our colleagues, Les, wrote a Triton variant of an RMS norm kernel as well. But I think at this point, like the compiler could probably generate like most of this, if I'm not mistaken. So just like worth double checking there. I can check. So I think back to here, like, okay, we didn't look at this utils file. Okay, this is just the checking if a feature is a nightlies. It's not too interesting. Let's go to the checkpointing stuff a bit. So, okay, so checkpointing is kind of like a deep space. I think Chani will know a lot more than me. I just want to comment on it briefly, which is that like if you've ever like, I don't know, like there's certain video games that when you play them and you're trying to save the state of the game, and if the state is big enough, like let's say you're playing Factorio, you're gonna end up waiting like a few minutes for the game to save. And having this be a blocking call is like really bad. And so I think like torch load and torch save are blocking, if I'm not mistaken. And so the idea with like DCP, which is, where is it mentioned here? Distributed checkpoint, yeah. Is like a few things. Like one is you can save checkpoints in an async way. And two, your checkpoint can be distributed over multiple machines. I guess, Janu, is there any more you want to comment on checkpointing?
Yeah, let me comment on that. The first is that basically in Torchtitan we're using DCP. Like it's interesting technique itself because it allows the like distributed, as the name tells, the distributed way of doing checkpointing. For example, if you have 8 GPUs, then you can just save 1/8 of the model rather than like an entire copy on each of the GPU or machine. And the other interesting is we support this, async mode. Basically, checkpointing would have several stages, right? The first is called the staging stage, which you takes the model from GPU to CPU. And the second is from CPU to your disk. And I think this async by default means that after you still have this waiting period, which you wait for the model to be copied from GPU to CPU. And then you can do your whatever computation because the CPU already has it. So the CPU would take care of the two disk process. But I think there's recently like this concept of zero head DCP checkpointing, which says you can even save you don't need to wait on the GPU to CPU one because after after the optimizer does step, now you have something you want to save. So basically, you start the process of saving it to CPU, but you're still doing the model forward. So you can do them simultaneously. As long as this GPU to CPU finishes before the backward starts, you have an authentic copy of what you just had, like just as what you finished from the last optimizer dot step. So all these are covered, these discussions are covered in this channel, discuss.pytorch.org, which we have a dedicated distributed category. If you just hit distributed, and then Torchtitan, there's a subcategory Torchtitan. Can you go to the, yes. And we have some interesting discussions to tell, to communicate how we're doing certain things. We plan to have more to the list recently. Now it already has async TP float 8 and checkpointing. So it's a bit more technical here.
So speaking of like, I mean, I very briefly looked into checkpointing literature, and I noticed like there's kind of fairly creative checkpointing policies people have. Like the most common one is basically every couple of steps, but then I've seen some papers where, for example, you only checkpoint on a crash. So you basically almost just like never checkpoint unless the job completes or the job crashes. But I guess like at least within this repo, I think here like the checkpointing is interval based, kind of like how Harsha suggests, right? And then interval type.
Yeah, I think what you described is part of, I would say, fault tolerance, which we don't have yet.
Interesting. Okay. And then interesting that the export D type is in float 32. Could you say more about this?
Oh, I don't know much about this, but I think it depends on like your requirement for precision. If you can tolerate smaller precision, then you can save a checkpoint with a less precision, which will save you time and memory. That's the idea. Because you know some training jobs don't require very precise D types.
I see. So Eric is asking, are the master weights still in FP32?
Yeah, by default, yes. And um, so basically the mixed precision is handled by FSDP by default. And the FSDP has two types, like several types. You can check GitHub issues on this topic. Basically, you can configure what parameter type you want to save and what do you do communication in. But by default, it's all FP32. Yeah.
I have a comment to make, and maybe this is a feedback that I saw on the distributed asynchronous checkpointing. The documentation is not that great. Most of the documentation is outdated, and if I just follow that, it does not work at all. So there is an enormous time sink that happens on the documentation that are very outdated on distributed async checkpoint. Any chance those can be updated, please?
I see. Yeah, thank you very much for the feedback. I think our team has been aware of that. I'll sync with them to see when that could be updated. Yeah, a bit unfortunate. Like there seems to be not enough communications of how good DCP is currently. I think we need to do more job over there. But thank you. Yeah.
All right. So let's see. Any more thoughts on DCP, or should I keep going?
I think you can keep on going.
All right. So this file is not particular. It's like basically just like all the configs that are available. So I mentioned in the beginning that like as you're using Torchtitan, you basically set up a TOML script, like a TOML file, and then just like run the llama train script. A lot of those configs you can see here. So also I've often seen as people are forking the code base, just adding like a couple of configs that are like relevant to them is quite helpful. So just I'm not gonna go through this, but like there's a lot, so you can just like go scan it on your own time. Okay, let's talk about float 8 for a second. So yeah, so I think we talked about float 8 brief. Actually, we talked about float 8, logging. We talked about metrics. We talked about metrics as well, which is just basically all the VRAM metrics. We also have support for like just pushing things to like either a tensor board or weights and biases or locally. So you can share runs. Optimizer support basically by default, and we only support Atom and Atom W, but if you want to add your own optimizer, it'll work. I guess like Johnny, have you noticed like people having to do a lot of work to get like a custom optimizer working with like the rest of the Torchtitan stack?
To be honest, I haven't heard a lot on this. Basically, if you're doing this typical type of first moment optimizer updates, it should be handled. And it's worth noting that most of them are like by default, it's handled by so those ops are handled using dtensor. So including the for each options. I don't know, like people can be creative in applying optimizers, right? For example, there are these second moment Newton method based optimizing strategies. For those, we'll have to see if we need more dedicated support for that. But I haven't heard a lot. But the Atom Mini paper is a good story on that. I believe it must be Torchtitan make it easy for them to apply a new optimizer to the distributed training. Yeah.
I think, let me see, Atom Mini. Yeah, this is them, right? I think. Examples. Oh yeah, they do mention Torchtitan here. Okay, yeah, they've literally copy pasted the whole code, right? Looks like, and deleted some stuff. This is very common how we see people use the repo, by the way. Just copy paste and delete. Interesting. Okay. Let me keep going. So profiling. Okay, profiling is interesting. I would say there's two important profilers. One is the PyTorch profiler, which will give you like speed metrics and communication metrics. And then there's the memory profiler, which is pretty instrumental if you're trying to debug OOMs. They're often just like a context manager where you step through them. So again, you can copy paste these functions as is and use them in your own jobs. Utils.py seems to be like a bunch of miscellaneous stuff. Let me see if there's anything interesting. Maybe actually, could you talk about the context parallel stuff here? Because like it basically create context parallel context, and then it's like this weird decorator, like maybe could you, and then it calls STPA. Could you maybe talk a bit about how this works?
Yeah, sure. So let's first talk about what is context parallel. So context parallel is the way that you do sharded computation when you do computation when your sequence dimension is sharded when you do large language modeling. It's useful when you have longer sequences when, for example, you cannot even fit a local batch size one on a single GPU. And the technical challenge is when you compute those attention layers, scale dot product attentions. You would need, for example, the QKV, and when they attend to each other, you would need the entire sequences to make the computation. So we're like the context parallel is about using this blockwise attention. There's an inner attention where you compute the KV, and like you keep only a sharded version of the KV and keep a queue, and you do this all-to-all or all-gather computations to each time only doing inner attention on one of the sharded pieces, and you basically roll it in a circle, and basically you finish all the computation. So the idea is based on the blockwise attention paper, and which is also called the ring attention. But so this is really, if you think about it, if you want to implement it, you would have a super long file or with full of distributed operations. And the goal, remember, our goal of PyTorch doing those parallelism is doing it in a model intrusive way. And the reason sometimes we choose different APIs, and this time we choose the context manager as the API. So basically, you would put in like, hey, here's my input, here's the labels, and please do context parallelism under the hood when I'm enabling this context manager. And this is the idea. And this get train context is because, for loss parallel, we need a context manager. For this context parallel, we need a context manager. Sometimes we need more than one, and get train context is just wrap it up in a single helper function. So we have every composable context managers together enabled.
Oh, I see. So the alternative would be you would need to add like 3 decorators, and then you have to have them in a specific order, otherwise things break. And so you chose to create your own, which looks like this.
So basically to hide the complexity a bit. Yeah.
I see. Yeah, otherwise, like I went through this earlier, like there's basically like some functions to get peak flops, colors, like clipping gradient norms, like just nothing too crazy. And I think that's pretty much it. Like I think we pretty much went through all of the code. Like there's a couple of more tests and scripts and docs. Like you can go to the docs here. There's a bunch of CI related stuff and testing related stuff that's probably not going to be super interesting. But yeah, I think we went through the whole code in maybe an hour, which is interesting. So yeah, I guess, Chanyu, any parting thoughts?
I saw like in the chat that people are also asking HSDP. Just want to briefly mention HSDP denotes. So FSDP is fully sharded data parallel, which means you're doing data parallel, but you shard your parameter weights. HSDP means hybrid sharded data parallel, which means you have a 2-layer storage system, and in the outside layer, like you would store. So suppose you have a big, like higher level of GPU organizations, and you store your whole model on each of the group. And within each group, you do FSDP. And the benefit is that this significantly reduced the ring size of your altogether, so that you only communicate within a small group. Usually, for example, on a single node, which is much faster than you do fully shard and doing this ring altogether across the bigger world size. This is assuming that your model can fit on a single node, for example.
All right. So if folks have more questions, please post them in chat. I do want to make one quick plug, which is that like if you enjoy GPU mode in general, the content that's on there, and if you enjoyed the things that Jianyu was talking about today, then we basically have a project Popcorn where you can work on training a large model in public to generate.
Yeah, sorry, I just have one more comments on Torchtitan. We recently I posted a vote for new features on the discussions of Torchtitan. This is a great opportunity for people, for the community to have an influence on what we do next. So I would encourage you to either vote on the existing features or propose new. Can you go to this 693 link? Yeah, so you can see currently the top ask is MOE. The second ones are multimodal and diffusion models. So it seems it gets pretty popular, and we're seriously considering to cater to whatever is asked.
All right, very cool. So like if you're potentially interested in also like working on the PyTorch team as a PhD intern, and you found these topics generally interesting, please apply to this job, and you can like reach out to me if you have any questions. The advisors here would be like Vincent Moines, who's the tech lead for TorchRL, Sumit, and the creator of PyTorch, and myself. So just like let us know if this is interesting to you. Otherwise, if you want to chat with Jianyu more, then oh yeah, let me copy paste the link. Otherwise, if you want to chat more with Jianyu about Torchtitan, we already put the discussions in the link. I think he's fairly active there and on Discuss, so just let us know if you need anything. And thank you, everyone. We hope you enjoyed this lecture. This is going to be the last lecture of the year. But next year, the first lecture will hopefully be Adam Pashke, which is the co-creator of PyTorch. And so we'll see everyone soon. Thank you so much.
Thank you, Mark.